Okay, so we're going to call this extension. Oops, let me get a pen. Extension. And what we're going to do is derive the equation. Deriving the equation for the period of a pendulum. Okay. So this is not something that you're going to need to be able to do in an exam, but it's something that will help you understand why the equation looks the way that it does. So, if we have a pendulum in mid-swing like this, this is going to be our displacement. This is the length of the pendulum. And we can draw a little dotted line here to show the equilibrium position. And we can call this angle here theta. So we can see from this that x over L should be equal to sine theta. Now, if we look at the forces acting on the mass, we have a weight force and we have a tension force. And if we add those two up, we'll get the restoring force, or the net force acting on the pendulum. So the weight plus the tension will be equal to the restoring force. In fact, I'll do that in a different color, because that's the interesting one. So this is the restoring force here. And this side here is mg, that's the weight force, and this one we'll just call tension. So here we can see that the weight force is the hypotenuse and the restoring force is this one. So we can say F restoring divided by mg, and this is going to be the same angle that we had before, because this angle here has got to be the same theta. So that should be equal to sine theta as well. Okay. Now we can write the restoring force. So now that we have all those equations, I'm just going to move up slightly. So we now know that x is equal to L sine theta, and we know that F net, which is the restoring force, is equal to mg sine theta. But we also know that the acceleration of an object is always equal to F net over m. So the acceleration of this object is just going to be g sine theta. Okay, so now we have an expression for x and an expression for a. For simple harmonic motion, a should be equal to negative omega squared x. And we also know that a and x are in opposite directions, so we need to make one of these things negative. So I'm going to say that because I drew the diagram like this, the displacement is going to be negative and the acceleration is going to be positive. Okay, so then we end up with g sine theta is the acceleration. That's from here, or so that's from 2. That must be equal to negative omega squared times negative L sine theta. Alright, so now we can cancel the sine thetas, and we can cancel these minus signs, because negative number times a negative number is just a positive number. So we get g is equal to omega squared times L. But omega is equal to 2 pi over the period. So now we have an expression relating the period, g and L. We should just need to rearrange it. So we get g is equal to 4 pi squared over t squared times L. So what I'll do is I'll multiply the t up here I'll do this in little steps. So we get t squared times g is equal to 4 pi squared times L. So t squared, if we divide both sides by g, is equal to 4 pi squared times L over g. And now if we just take the square root, we get t is equal to 2 pi times the square root of L over g. And so that shows where the equation comes from, and this is the equation that we need to be quite familiar with using.